Hello and welcome back to the Science of Concrete Materials class. This is lecture number 23 of the class, and today we are going to start on a new module, which is the aggregates. Okay, aggregates generally occupy about 70 to 80% of the volume of the concrete. And based on that, they are expected to have an important influence on its properties. So what they basically are granular materials derived from, for the most part, from natural rock, such as crushed stone or natural gravels and sands. But, synthetic materials such as slags, expanded clay or shale are also used to some extent, which basically mostly in lightweight concretes and the like. So for aggregates, in addition to their use as economic filler, they generally provide concrete with better dimensional stability and wear resistance. Dimensional stability means volume changes. The influence that the aggregates can have on the mechanical and physical properties of the concrete are listed in the table I will show on the next slide. These influences on the physical and mechanical properties will be discussed in later classes, okay? Here in this discussion, we will discuss the influence of aggregate properties on mix design and special durability problems associated with aggregates, okay? So as you can see here in this table summarized, what are the properties of concrete influenced by the aggregate properties, such as durability, for example, to freeze, resistance to freezing and thawing, and what is the relevant aggregate property that we should be looking for: porosity, soundness, permeability, degree of saturation, something like this. For strength, for example, the strength of the aggregate, the surface texture, the cleanness of the aggregate, the particle shape, maximum size, all these influence the strength of the concrete. For example, shrinkage and creep, modulus of elasticity of the aggregates, their particle shape, gradient, cleanness, maximum size, presence of clay minerals within these aggregates, all those properties of the aggregates will influence, for example, shrinkage and creep of the concrete, and so forth and so on. And you can see here, a list of every property that could be influenced by the presence of the aggregates. So the aggregates are, the moral of the story. The aggregates, they are an economic filler in concrete because they constitute about 70 to 80% of its volume. But their properties are also important to the properties of concrete. Making basically good concrete requires good aggregates. Okay, so in this module, the topics that will be covered, of course, we're going to have an introduction about aggregates, which we are discussing, classification of aggregates, geological origin, which we're not going to discuss in depth, we're just going to mention it, size, weight, properties of the aggregates, such as shape, texture, size gradation, moisture content, specific gravity, and bulk unit weight. And also we are going to discuss the effect on concrete property, fresh and hardened, okay? So let's get to it. So, okay, so although, as we said, although aggregate strength, can play an important role in high strength concretes, for most applications, The strength of concrete and mix design are essentially independent of the composition of the aggregates, okay? So durability, however, may be affected. So there is no particular rock or mineralogical type in itself, is required for aggregates, but it has been found that some constituents may cause problems in the field, as we will see later. And as I mentioned in that table just a minute ago. So in other instances also, a certain kind of rock may be required to attain concrete properties, for example, high density or low coefficient of thermal expansion. Those things may be required for certain applications. But in the absence of special requirements in general, most kinds of rocks can produce acceptable aggregates that will conform to ASTM C33, which we will discuss later. So aggregates are not generally classified by mineralogy. The simplest and most useful classification is on the basis of specific gravity, as we will see later. So the geology of the rocks where the aggregates come from will not be considered in this class, only briefly mentioned. The ASTM C294, though, describes, principal rock types and constituents for common aggregates, if you need to look at that for more details. Okay, aggregates also are classed as heavyweight, normal weight, and lightweight. Most of this discussion in this class is devoted basically to normal weight concrete, aggregates rather, which make up about 90% of the concrete produced in the United States and Canada, since, basically the same considerations apply generally to other weight classes. Aggregates, again, just general about aggregates, they should be hard and strong, free of undesirable impurities, and should be chemically stable. Soft, porous rock can basically limit the strength and wear resistance of the concrete. It may also, break down during mixing, and which will adversely affect workability by increasing the amounts of fines and other undesirable results. Rocks that tend to fracture easily along specific planes, flaky stuff, can also limit strength and wear resistance. So it is best to avoid aggregates that contain significant proportion of weak or friable materials, or at least to remove them. So aggregates should also be free of impurities such as silt, clay, dirt, or organic matter. All right. So if these materials, if these materials are not removed, if they will, if they coat the surfaces of the aggregate, they basically will isolate the aggregate particles from the surrounding concrete, causing a reduction in strength. For example, silt and clay and other fine materials will also increase the water requirements of the concrete, and some organic matter may interfere with the cement hydration. So there are standard tests, used in the United States to evaluate aggregates, as might be discussed later. Okay, so we talked about the classification of the aggregates. Let's just define or name the classification used for the aggregates. First, according to the geological origin, we have the igneous rocks, sedimentary rocks, and metamorphic rocks. okay, or according to size. For example, we have the distinction between, coarse aggregates, which are predominantly retained on the number 4 sieve, the 4.75 millimeter sieve, and the fine aggregates or sand, which are the aggregates passing the number 4 sieve and predominantly retained on the number 200 or the 75 micrometer sieve. Okay, we will look at the sieve analysis later. Okay, so also aggregates could be classified according to their unit weight. So we have the, as I mentioned in the introduction, we may have lightweight aggregates. So we have the lightweight aggregates, which is the unit weight of the aggregate is less than 1,120 kilograms per cubic meter. The corresponding concrete using this aggregate, has a bulk density less than 1,800 kilogram per cubic meter. And basically, the source of these are the cinder, the blast furnace slag, or the volcanic pumice. We have the normal weight aggregate, the aggregate which has a unit weight of 1,450 to 1,750 kilogram per cubic meter. The concrete made, with this type of aggregate basically has a bulk velocity of 23 to 2,400 kilogram per cubic meter. These, like I said, this is, the 90% of the concrete produced is the normal weight concrete. We have also the heavyweight aggregate. The unit weight is greater than 2,100 kilogram per cubic meter. The bulk density of the concrete, corresponding concrete using this aggregate is greater than 3,200 kilogram per cubic meter. So a typical example is the magnesite limonite, which is, or a heavy iron ore basically. The heavyweight concrete is used in special structure, such as radiation shields and nuclear plants and something like that. This slide here shows, a graph of the available rocks, with their origin, unit weight, related use in concrete with its unit weight and compressive strength. Just this is a good summary to give you an idea of what is out there about as far as the aggregate, and the corresponding concrete. What are the properties of this concrete and where it is used, as you can see. Okay. Okay, so let's look at the properties required for mix design for the aggregates. So in order really to proportion a suitable concrete mix, certain properties of the aggregate must be known, such as the shape and texture, the size gradation, moisture content, specific gravity, and bulk unit weight. These properties, influence the paste requirements for basically a workable fresh concrete mix. So these must be determined in order to perform a mix design. So let us look at these properties and their effects. Okay, so as I said, we have the shape and texture. We'll see the effect on workability and on the mechanical properties. Let's see what's the effect of the shape and texture on workability. So an aggregate shape and texture affect the workability of fresh concrete, given, through basically their influence on the cement paste requirements. So sufficient paste is required to coat the aggregates and to provide basically lubrication to decrease interactions between the aggregate particles during mixing. Okay, for good workability, the ideal aggregate particle is one that is close to spherical in shape, well-rounded and compact, with a relatively smooth surface, as shown in this figure right here. Most natural sands and gravels come close to this ideal, but the remaining types may not, though. But this is the idea. We want good workability. Basically, we need to reduce the friction between the particles, and we need less space to coat the particle in order to have a workable mix. Basically, also keeping economy in mind with less space. Okay, these are the possible shapes that you will get. You have the spherical, the rounded shape, the rounded, spherical, irregular, flat, or elongated, and we have the angular particles that could be any variation of these shapes, and these, of course, will be more difficult than the rounded one in terms of workability. As I said, crushed stone is much more angular with sharp edges and corners, and may have a rough surface texture. Such particles interfere more severely with the movement of the adjacent particles, even when nearly uniform in shape. Even when they are, if they are uniform in shape, these angular rocks will have more interference with one another, and of course they will affect the movement of the other particles. They also have a higher surface to volume ratio, and therefore require more paste to fully coat the surface of each particle. Economy. These highly irregular particles especially with reentrant faces and sharp points will lead even to greater interparticle interactions during mixing and handling. Okay, so the shape, if you can control the shape of the aggregates should be closer to that ideal shape, but of course that's not always the case. The aggregates that are flat or elongated should be avoided because they increase interparticle interaction and the surface to volume ratio, thereby increasing the paste requirements. Also, concretes containing aggregates of this shape are more prone to segregation during handling, so you have to keep that in mind. Also, the presence of flat or elongated particles in crushed rock may be indicative of rock with weak fracture planes, and again, that's something also should be investigated. So the surface texture of the aggregate is also important for workability, since rough surface requires more lubrication for movement, which is more paste. The crushed stone has, a rougher surface than natural sand and gravel because the surface has not been, worn smooth by the effects of the water and the weather. Okay. Basically, there are no specified tests or detailed definitions prescribed by ASTM for surface texture, and particle shape. So although ASTM C1225 does promote an indirect measure of both by measuring their effect on the void content of fine aggregate, but there is no such specified test for this property. However, though, a British standard has a classification system, as I will show on the table on the next slide. which basically provide some useful information with regard to shape and texture. And here it is. So here, these basically the shape classification and surface texture of the aggregates, for concrete. These are the types we talked about and their description and examples of them. And these are the surface textures, characteristics of each texture and examples of the rocks of these things. Okay, so basically with the discussion, the preceding discussion with this, you could have an idea about, rock texture and shape and how that will impact your concrete mix. Okay, so as far as the effect on the mechanical properties, of the shape and texture, the characteristics of the aggregates, may affect the mechanical properties of the concrete, basically by affecting the mechanical bond. By increasing the surface area available for bonding with the paste for a given content, but in extremes in aggregate, shape may lead to high internal stress concentration and lower the strength eventually. The rough textured surfaces will improve the mechanical component of the bond because they, bond better. It is also thought that, the mineralogical character of the aggregate can play a role in determining strength of the aggregate, paste bond, since, a chemical interaction may occur at the interface between certain kinds of rock and the cement paste. And again, that's something also should be investigated. Okay, so let's look at the size gradation. I'm going too fast here. Let's look at the size gradation. So the particle size distribution or grading of an aggregate supply is an important characteristic because it determines the paste requirements for a workable mix, as we will see later. Basically, since cement is the most expensive component, it is desirable to minimize the cost of the concrete by using the smallest amount of paste, basically, consistent with the production of a concrete that can be handled, compacted, and finished, and also provide necessary strength and durability. So we want to use the least amount of paste possible while all meeting whatever requirements we are supposed to meet. So the significance of aggregate gradation is best appreciated by considering, concrete as, a slightly compacted assembly of aggregate particles bonded together with cement paste, with the voids between the particles completely filled with paste. Okay, so the amount of paste depends on the amount of void space that must be filled and the total surface area of the aggregate that must be coated with the paste. That's how you look at it. So the volume of the voids, between the, let's look at the, okay, so the volume of the voids, between roughly spherical aggregate particles is greatest when the particles are of uniform size. Look at it. These are uniform size particles. So we have the voids as basically the largest or the greatest in this case. So it requires a lot of paste to coat all the aggregate particles. Okay. So when we use a range of sizes, the smaller particles, as you can see here, the smaller particles can pack between the larger particles, as shown here, okay? And, basically, by doing this, we decreased, the void space between the particles, and we lowered the paste requirement. Okay. Furthermore, also what we can do, basically, sometimes if we use a smaller maximum large, if we look at these, for example, if you consider this the maximum size aggregate, if we reduce this maximum size aggregate, we replaced it by smaller aggregates, then in this case, actually what we did, we increased the void space, and we will require more paste to coat all the surfaces. So the maximum size aggregate to be used, first before that, the gradation, the aggregates have to be well graded, as we will look at that in later lectures, in order to end up with the least possible voids between the aggregates, of course, while maintaining other requirements in mind. Okay, so well-graded aggregates will provide that minimum void spacing that will be needed to be coated by the cement paste, requiring the paste requirements by doing that. So, but as we will see later, and for a given maximum aggregate size, there's a theoretical grading curve for minimum void space that basically can be worked out using simple geometries, as I mentioned. I just summarized what I mentioned. So such size distributions do not give a workable concrete. A compromise basically has to be worked out between workability and economy. So as I said, we need to compromise between workability and economy, and this is different for each maximum aggregate size. As you can see, the maximum aggregate size here is smaller than this. We ended up with more voids. So again, when we look at the gradation curves, the picture probably will be clearer. Those two cases here, one is called gap graded aggregates, and this one no fines aggregate. We will talk about these two when we discuss the grading curves. Okay. Okay, so let's look at the size analysis. With the size grading, we talked about the texture and shape. We talked about the size grading, size gradation. Let's talk about the size analysis. So the particle size distribution or grading of an aggregate supply is an important characteristic, as I said, because it determines basically the paste requirements for a workable concrete, as I mentioned. So basically the grading of an aggregate supply is determined by a sieve analysis. A representative sample of the aggregate is, basically passed through a stack of sieves, arranged in order of decrease in size of the opening of the sieves. So it is convenient, though, to divide aggregates into coarse and fine fractions. So the coarse aggregate fraction is that retained on the 4.75 millimeter sieve, which is the number 4 sieve, while the fine aggregate fraction is that passing the same sieve. Okay, that's the distinction. The common sieve size I will show, in the table on the next slide. I'll show it in a minute. The standard, sieve designation is based on the nominal opening in basically millimeters or micrometers, as you can see. Or the alternate designation is based basically on the size of the openings in inches for coarse sieves, and the number of openings per inch of the fine sieve. As you can see here, this is the alternate designation and this is the ASTM designations. So basically this is for coarse aggregate. This is 75 millimeter sieve. Basically the size of the opening is 3 inches. Okay, and this one here, the number of as we said, in the fine aggregates will be the number of openings per inch in the, for the fine sieves, right? Okay, so when we say number 4, this is number of opening 4 per inch, okay? Or just basically the nominal opening in the ASTM designation. So this is the ASTM designation, this is the alternate designation, okay? So it can be seen, also that, each sieve used to grade the fine aggregate has openings that are half the dimension of the next one. As you can see, this is half, and this is, considering 1000 micron equals 1 millimeter. So this is about 1200. So, and this is 600, half of that, and so forth. Okay. And the coarse sieves, the ones that fit in the size sequence of, for example, 9.5 millimeter, 19 millimeter, 37.5 millimeters, and 75 millimeters. 3 in inches, 3/8, 3/4, 1.5, and 3 inches. Okay. The sieves that, in this size sequence are in the standard series. The other, are called basically half sizes. Okay, so that's something to know about the ASTM sieve sizes, the commonly used for sieve analysis. That's something to know. Okay, there is also something in the gradation, the size gradation, something called maximum aggregate size. The maximum size of the coarse aggregate, as I mentioned earlier, influences the paste requirements of the concrete and also the optimum grading of the coarse aggregate depends on the maximum aggregate size, as we will see later. So as defined by ASTM C125, the maximum size of coarse aggregate is the smallest sieve opening through which the entire sample passes. Simple, okay? In practice, however, it is considered that if only a small amount of aggregate is retained on a sieve, it will not significantly, basically affect the properties of the concrete with 5 to 10%. So it is usual to use a nominal maximum size, which is the smallest sieve opening enough which the entire sample is permitted to pass, but need not do so. So a percentage of, usually, as I said, 5 to 10% of the sample weight may be retained on this sieve. Okay, so when we say 95% passing or 90% passing, this is practical for nominal 100%. The ASTM grading requirements are based on this nominal maximum size, okay? Also, the choice of a nominal maximum size, maximum aggregate size is determined by job conditions. Listen to this. If the aggregate size is too large, the concrete at any given cross-section of a member may not be basically representative of the entire material, because of the location of an overly large aggregate particle. Basically, you might end up with just aggregate in certain cross-sections, as I will explain in a minute. So basically, to guard against this possibility, the maximum size should not be greater than one-fifth of the smallest dimension between the sides of the form. For example, if you have a wall, you have a section of a thin beam, so the maximum aggregate size should not be should not be greater than that 1/5 of the smallest dimension of the beam, the width of the beam, for example, or a wall. For slabs, this figure may be relaxed to 1/3 of the thickness. Okay. Large aggregate particles may also get obstructed at narrow openings between reinforcing bars. So again, we have to take some precautions, or there are certain measures need to be taken. Or between bars and formwork, which is the clear spacing from the formwork to the bar. And by this, they will cause undesirable segregation during placement. To avoid this problem, the nominal maximum size should not exceed 3/4 of the minimum clear spacing between reinforcing bars or between reinforcing bar and the forms. Okay, so we have those two criteria when selecting maximum aggregate size, especially for reinforcement concrete members. So basically these two requirements, if you look at them, will effectively limit the maximum size on most jobs to 40 millimeter, which is the 1.5 inches or less. Okay, so larger sizes can be used in unreinforced concrete, mass concrete, where the limitations on size do not apply. Okay, so most equipment in the concrete and the ready mixed concrete industry can handle up to 50 millimeter or 2-inch maximum aggregate size, but equipment used in mass concrete construction can handle up to 6-inch or 150 mm coarse aggregate, where the larger volumes of concrete justify basically the use of the larger equipment needed, for these aggregate sizes. Okay, but most equipment, for testing concrete is designed to handle only up to 37.5 millimeter aggregates. Okay, so the maximum size aggregate of this range, 37.5, as you probably will notice. So larger sizes must be screened out before testing, and you have something to be aware of when you have. Most jobs you will work on, other than the unreinforced mass concrete, you will not see more than this maximum, 37.5 millimeter aggregates. Okay. Okay, so let's continue about the maximum size, maximum aggregate size. The higher the maximum aggregate size, the lower the paste requirements for the mix. Okay. Refer back to those earlier schematics I've shown. For a given workability and cement content, the strength of concrete increases with increasing aggregate size because the water cement ratio can be lowered, as we will see on this figure. I'll talk about it. Okay, for concretes with low cement contents, which are typical of mass concrete, they show continuing increase in strength with the increase in size. These are low cement contents mixes. Generally though, an increase in the maximum aggregate size will improve concrete durability because there will be less paste. Remember, I made this statement before. There will be less paste subject to chemical or physical attack. Okay? But if an aggregate is, for example, susceptible to freeze, thaw damage, a reduction in aggregate size will improve durability, as we may see in the durability discussion. So like I said, there is always more than one side to the story, and there is always a compromise that has to be made between various properties: strength, durability, economy. And your role as an engineer, you have to be aware of all the factors that impact whatever job you are working on, in terms of whatever you need to decide. You need better workability, you need more strength, you need less cost. Of course, durability is always a key. So there are always many factors, many variables to consider. And I said, there is always a compromise that can be made and fulfilling all requirements. Okay, so let's look at this figure here. As you know, as discussed, strength increases as aggregate size increases. As you can see here, for example, here and here. But there is always a but though. With the larger aggregate sizes, increased stresses tend to lower the strength. This is most noticeable only in rich mixes. What is a rich mix? A rich mix that contains a high proportion of cement. A lean mix, on the other hand, a mixture of concrete or mortar with relatively low cement content. There is another term that you probably related, we should just talk about it, which is the harsh mix, which is one without mortar or aggregate fines, basically. And it has certain problems. But let's go back to our discussion. As I said, with the larger aggregate size, increased internal stresses tend to lower the strength. And I said this is most noticeable in rich mixes with high cement proportion, okay? So if the water-cement ratio is not lowered, the strength will drop with an increased maximum aggregate size. So again, when I was talking about compromise and being aware of whatever requirement, if high strength, is a requirement of a job, then maximum aggregate size might have to be dropped. You might have to settle for a lower maximum aggregate size. As a result of what I just said, achieving high concrete strength, in the range of 70 MPa or 10,000 psi. In that case, we may be required to use a maximum aggregate size of maybe 9.5 millimeter or 3/8 of an inch, because with the high cement contents, other factors need to be considered. Okay, so as I said, there is always a compromise that needs to be made between economy, workability, strength. Of course, strength cannot be compromised if it's required for a job, but what I'm saying is, as a design engineer, you have to be aware of what's available or what can be done, and listen, at what cost. Okay, that is the missing key of the equation for many of the engineers I have worked with. Anyway, I will stop here for now. So this will be the end of lecture 23, and we will continue next time. We will talk about, we will continue our discussion on the properties required for mixed design, the size gradation. We will talk about next time grading curves. So until then, thank you for watching, and I will see you next time.